So let me make the introduction first. So hello, everyone. Welcome to this Young Achiever Seminar. So my name is Wenbo Zhang. I'm a second-year PhD student in IST. In this semester, I'm helping the Center for a Socially Responsible AI in Penn State to organize this talk series. So today is our fourth talk. We are happy to have Christine, a senior PhD student from the University of Maryland, to share her research. Her research focuses on sequential decision-making and uncertainty, algorithmic fairness, knowledge representation and reasoning, and healthcare. So for today's talk, we will have two parts. In the first session, Christine will share her research at first, and then in the second part, we will have a 5 to 10 minutes Q&A session. So shall we start, Christine?
Sure. Thank you so much, Wenbo, and thank you as well to Penn State for the invitation. So the title of my talk is Incorporating Prosocial Constraints and Exploiting Problem Structure in Sequential Decision-Making. Sorry, one sec. And before I get started, I'll just give a brief overview about my own background. So I am a CS PhD candidate at University of Maryland. My advisor's name is John Dickerson. And some of my research interests include sequential decision-making, so things like multi-arm bandits and reinforcement learning, algorithmic fairness and its many manifestations, particularly as we'll see here today with respect to resource allocation. And I often look at applications in healthcare, whether it's thinking about incentives, so sort of an economics approach, or informatics, so sort of unsupervised learning and trying to identify patients with complex diseases. During my PhD, I've had the opportunity to intern at Amazon Robotics, Microsoft Research, and Google Research. And prior to grad school, I had several years of experience doing quantitative research, generally with domain focus in macroeconomics and healthcare. In my talk today, I'm going to speak about two works. The general focus is on constrained resource allocation. In the first work, I'll talk about this setting with fairness guarantees. And then the second setting, I'll speak about this problem when we think about allocation within communities. So the general problem that we consider is we have some set of individuals, and the states of these individuals are changing over time. And we also have access to some set of interventions that increase the probability of an individual experiencing a desirable state transition. And the question—
Sorry to interrupt, Christine. Doesn't look like your screen has changed. It's still on the first screen title screen. Is that what you intended?
No, sorry, it should, for me, it's changed. I'm not sure why.
Maybe you have a different display.
Yeah, the slide title should be Overview, Constrained Resource Allocation.
No, we're still seeing the title slide.
Okay, give me a sec. So, let's troubleshoot for a second.
Yeah, now we see
good now?
Overview, Constrained Resource Allocation. Yeah.
Okay, I'm not sure if that will change once I go back to full screen, but let's give it a shot. Okay, do you all still see the overview slide?
Yes.
Perfect, okay. So the general question that we're trying to consider here is how can we best allocate these interventions? Meaning we have some fixed amount of them to provide, and we want to do so efficiently such that the community as a whole and the individuals contained within it derive best possible benefit. So as a motivating example, we consider chronic disease management. So in this type of setting, we have some set of patients, and they're trying to adhere to some type of chronic disease management or lifestyle program. So it could be something as simple, for example, as getting daily exercise, making change to your diet, using a CPAP machine if you have sleep apnea, taking your medication if you're a tuberculosis patient. There are many examples in the literature, and we sort of just consider this broad setting. And if you're a decision maker in this setting, your goal is to ensure adherence. Oh, please go ahead, Shyam.
So it looks like if the slide is not changing. We are still on the overview constraint.
Okay. So I'm going to go out of full screen because it seems like for some reason we have an issue. Are you able to see the motivating example slide now?
Yes, now we are seeing that.
Okay, so sorry, I don't know why that's happening, but we'll just—
You want to go to the next slide and just test it while we are in this mode? Yeah, now we see the next one as well. Multi-arm bandits. Okay,
yep.
Cool.
Cool. Okay, so we'll just stick with the slightly smaller view. Apologies for the technical difficulties there.
For us, it's the same. We get to see it doesn't make any difference, full screen or what.
Okay, perfect. Okay.
It didn't go to full screen actually. Your slide are staying, even if you go to full screen, it's staying in the same. That's why it was not changing.
Yeah, I guess that's what I mean. I've reduced the window now, so hopefully the transitions are happening. But of course, let me know if that's not the case. So for our decision maker in this constrained resource allocation setting, your goal is to ensure adherence, and generally you have some budget constraint, meaning you might have access to an intervention that makes everybody more likely to adhere. For example, if a doctor calls your house every day and tells you to exercise, the probability that you will exercise might increase, but you can't afford that because doctors are expensive, right? Additionally, we have engagement risks. So if you harass people or constantly nudge them to change their behavior, you may actually have an unintended consequence where they no longer want to receive notifications or just engage in the program at all. So these two things taken in tandem motivate efficient allocation of the interventions that we have among the patient population. So the problem that I've just described has been modeled using the restless multi-arm bandit framework. So I'm just going to walk through some of the background on this framework before I go through how we might apply it to the particular settings that we care about. So in contrast to multi-arm bandits, which some people might be familiar with, where you're generally looking at arms with fixed reward distributions, in the restless bandit setting, our patients correspond to what are known as arms, and each arm is represented as a Markov decision process. So each of these Markov decision processes, or MDPs, can be formalized as follows. So we have a state space, S, and we generally consider a simple binary state space where the states can be ordered by desirability, such that we have our 0 is like our sad face, or in this case, the case where you don't adhere. And the desirable state, or state 1, is where you do adhere to the particular behavior modification. We also look at, in the traditional setting, a binary action space, where 0 corresponds to not providing an intervention. In the literature, this is referred to as a pull, where, and conversely, 1 represents the decision to provide the intervention to a particular person. We also have a cost function, which maps our actions to real values. In general, it costs 0 to not do anything, and the cost of a pull is unit full. We also have a transition function, which maps the cross product of state and actions to states, which just tells us, how likely you are to transition to one state given that the state you were in at time t and the action that was taken. Finally, we have a local reward function. We specifically consider the identity function, so we just map from state to real values, as a reflection of the state. However, the claims that I'll make in the rest of the talk hold for any local reward function that is non-decreasing in S. And this is just consistent with the fact that we're trying to assign reward when you're in the desirable state. And if you're this decision maker in this context, you're looking for some policy, pi, which is a mapping from states to actions, that maximizes total expected reward, so cumulative over time steps as well as over the population. And you also want this policy to satisfy a per time step budget constraint, which in the case where we're talking about pulls just means you can only pull K arms at each time step, and K is generally going to be significantly less than the total population N. We also assume some structural constraints in this setting, and there's some motivation for these which come from the domain. We specifically assume non-zero transition entries, and we also impose some structural constraints. The first of these equations just implies that an arm is more likely to stay in the desirable state than it is to transition there from the undesirable state. So essentially, if you're someone who likes to exercise, you're more likely to exercise than someone who doesn't exercise at all, like spontaneously deciding to one day, for example. The second constraint set just implies that messages or really any action that's not nothing is beneficial when you receive it, and that we can define some strict preference relation over actions, and that this holds for every arm. And this constraint in particular is just consistent with our optimization objective being to maximize allocation. If the intervention was not beneficial when received, we wouldn't be concerned at all, right? We'd want to actually take it away rather than provide it. So background about how these problems have been solved historically, it's proven that pre-computing the optimal policy for a given set of restless arms is p-space hard. So that's bad news from a complexity perspective. However, when arms are indexable, it is possible to decouple them, and this allows us to consider a Lagrangian relaxation of the original problem. And this comes from some foundational work by Whittle as well as Weber and Weiss. Essentially, Whittle has proposed what is now called the Whittle index. And we could think about the Whittle index as the infimum subsidy, M, that a given arm would require to be indifferent between a pull and passivity given its current state. So we're basically saying, I'm not going to give you this beneficial thing, this pull. However, I'm going to subsidize your lack of receipt of a pull. How much subsidy do you require to be indifferent between them? You can then order the arms by the subsidy required and choose the top K arms. So essentially you're choosing the K arms with the highest opportunity cost of passivity. However, there are some core limitations of Whittle index-based policies, and the work that I'll present in the rest of the talk addresses each of these limitations in turn. The first is that Whittle doesn't provide any type of distributive fairness guarantees, meaning we don't get any guarantee about how pulls will be distributed among arms. And we're thinking, arms represent people, so it's worth it to think about the arms as having agency in the setting we consider. The second limitation is that we're not able to exploit spillover effects when the resource in question is allocated within a community. So Whittle just treats arms as independent, and that's actually where it derives its efficiency from an algorithmic perspective. We're not able to take advantage of the fact that in many cases, if you give someone a resource, their neighbors may receive indirect benefit. So we'll start by looking at the fairness issue. So the papers that I'll sort of cover these themes under, the first one, the algorithm is called ProbFair. In ProbFair, we present a constrained reward maximizing policy, and it's guaranteed to satisfy probabilistic fairness and budget constraints. And the second, which addresses resource allocation over communities, is Greta. So Greta is a graph-aware Whittle index-based heuristic algorithm, and we're able to construct a reward maximizing mapping from arms to actions at each time step. So let's start with fairness. So Whittle index-based policies, as I said, right, we don't have any guarantees about how pulls will be distributed. And in fact, it's not just that we don't have any guarantees, is that empirically, we actually see that they produce a bimodal allocation. So what that means, right, we have some time horizon T, some budget constraint K, and our Whittle index policy will allocate a majority of our T times K available pulls to a small subset of arms represented by these blue crosses in the graph, and it will ignore the rest of the arms represented by the red X's. So in the plot here on our X-axis, we have the arm rank by the number of pulls that a given arm receives over all runs. And on the Y-axis, we've got average number of pulls received, over T by arm. So we can see that the vast majority, in fact, 7 of our 10 arms don't get any pulls in expectation. And we see a very small minority, these 3 arms in blue, get a vast majority of the pulls. So why does this happen, right? It's not random. We've done a lot of experiments and we can show that this holds across cohorts, across different transition matrix entries, provided that they satisfy our structural constraints. In fact, it has to do with the mechanics of Whittle itself. So the structural constraints ensure that the intervention benefits every arm. However, the degree of marginal benefit varies among arms. For example, if the intervention in question is a phone call from your doctor reminding you to eat your vegetables, some people may be really responsive to that and might change their diet the day that they receive a call. Other people, may not matter how much you call them. They're really resistant to change. So the fact that we have scarcity in the form of our budget constraint, coupled with the fact that we have heterogeneous transition dynamics, because we don't place any constraint on homogeneity with respect to arms, may favor some arms over others, and this yields the skewed bimodal distribution that we observe. So to support this, we have a simulation result here, where we have 2 arms, and regardless of how long each arm goes without a pull, this is basically the probability that it will be in the good state, given that it was last observed at some number of time steps that's increasing. We look at the Whittle index values, right? Regardless of the last observed state, we see that the red arm here, for any any state is always less than the blue arm, which means if we have a budget equal to 1, we will pull the first arm at every single time step, and the red arm will never be pulled. So what does this mean, right? If we think about ethical and pragmatic concerns that might arise as a result of this bimodal allocation, particularly when we think about healthcare as our motivating example. So Whittle is utilitarian, which means that we're maximizing total expected utility. We do not care, and in fact, nothing in the algorithm encodes any respect for distributive fairness. Now, practitioners may be inclined to favor more egalitarian approaches like round robin, where you just allocate pools sort of in a circle over the population. So that gives you an equal allocation of the resource among arms, but it completely disregards total utility, and in particular, the difference in marginal benefit that occurs among the population. So we have these two sort of polar opposites of how we might structure our allocation algorithm. And our objective that we consider is how can we improve the outcomes, right, and ensure that participation is rational in expectation for these arms in red here that would receive 0 or perhaps even negative expected value of participation under the status quo. So this is something that we can think of as a prioritarian alternative, where the group that we're prioritizing is the group that would be denied algorithmic attention under the status quo. So how might we do this? There are sort of two things that we consider. The first is time index fairness. So this type of constraint would just require that each arm is pulled at least once within some time interval, or a slightly looser version, a minimum fraction over all time steps. The second type of constraint that we might consider is probabilistic. So this is just basically saying that the probability that any arm I receives a pull at any time step must fall within some user-defined interval, L, U. And we impose some constraints here. So we require L to be strictly greater than 0 and less than or equal to K over N, which is in turn less than or equal to U, which again is less than or equal to 1. So essentially we're trying to say that you get a strictly positive lower bound by virtue of participation. You are guaranteed to have some benefit. So among these two constraints, if you're a practitioner, the time index version might be more desirable. It's a little bit more interpretable as well. However, unfortunately, it's not possible to modify the Whittle index to guarantee time index fairness without sacrificing tractability. So why is this the case? Essentially, we're able to, asymptotically optimally solve this p-space hard problem using the Whittle index because it allows us to decouple arms. However, when we think about time index fairness, we need system state. We need to know not only, have I gotten a pull in the past series of time steps, but who else has gotten a pull? So you introduce this exponential dependency, and you can only tractably solve that for very small problem instances. At scale, it's not possible. However, if we consider probabilistic fairness, it is possible to derive the policy that satisfies that definition via a relaxation. So we define this policy, which we call pi PF or prob fair, and this is essentially a mapping from arms to probability distribution. So we have this term P sub I, which is the probability that an arm will get a pull at any given time step. And of course, 1 minus P sub I is the probability the arm won't be pulled. Importantly, this mapping is stationary, meaning that it doesn't change over time. We have our constraints and our inequality that the values L and U are required to satisfy. And we observe that because our policy is stationary, if we repeatedly apply it, we will converge to a steady state in which any given arm I is in the adherent state, so the good state or state equal to 1, with probability X sub I in the interval L, U. We can then essentially construct a constrained reward maximizing objective where we're trying to solve for the P sub I's, like again, the mapping from arms to probability values that maximize our objective and satisfy our budget constraint. So this is the relaxation that we consider. And how might we go about constructing this mapping, right? So we have a theorem in the paper 2.41, which essentially states that for every arm, f sub I of p sub I is either concave or strictly convex in all of p sub I over the interval 0 to 1. So we start by partitioning the arms according to the shape. Then we sort of look at the set of values that we're going to consider when we try to decide, all right, how much approximately optimal share of our total budget K are we going to allocate to the set X of concave arms? And it's approximation because we have this epsilon term here. Then for every candidate Z, which are again the set of values that we're looking at for how to allocate budget, we can solve P sub 1 by gradient descent. And we can solve P sub 2. So we have a lemma in the paper which tells us that the optimal solution to P2 will set some number of arms to L, at most one arm to P prime, which is in L comma U, and the remaining arms to U. So the reason that we don't just partition LU strictly is due to the approximation error and in some cases divisibility, but we're guaranteed to get at most one arm that's sort of in the middle there. So we develop a sorting procedure, which we outline in the paper, which allows us to construct this mapping. Then we sort of loop over our candidate values and we look at this objective function. We're basically saying, okay, for this mapping from arms to P sub I, what is our value function? We choose the Z, the candidate Z, that argmaxes that function. So that's our Z star here, the bottom of the diagram. This in turn yields a mapping from arms to probability values. Now we still need discrete actions at each time step. So we use a dependent routing algorithm from Srinivasan et al., which essentially allows us to sample from this probability vector at each time step in a way that satisfies our budget constraint and ensures that the probability that any given arm receives a pull is exactly P sub I. So theoretical properties of this algorithm, prob fair is constrained reward maximizing. It's subject to, again, the guaranteed satisfaction of fairness and budget constraints. The first claim follows from how we construct it and the fact that we require L to be greater than 0. So that brings us back to our claim of, having a strictly positive floor for participants. The second claim follows from the properties of the rounding algorithm that we use. And finally, when we look at runtime, prob fair is efficiently computable. So we have a sort of nested runtime here. So the outer loop is the cost of our grid search. The inner loop, the orange term, is the cost of solving P sub I, given some approximation error epsilon. And the blue term here is the cost of solving P2, which is dominated by sorting. So when we look at empirical results for this algorithm, we compare prob fair to a couple of different policies. The first is threshold Whittle, which is a state-of-the-art fairness agnostic algorithm. We also look at risk-aware Whittle. So this is built on threshold Whittle, but it incentivizes rather than guarantees fairness via a concave reward function. We also look at some heuristics. So these are basically varying the availability of arms based on whether they've had their constraint satisfied or not. So as you go forward in time, only arms that have not yet satisfied their constraint will be available. They don't give us any theoretical guarantees, but they do satisfy fairness. We also look at some baselines, random, round robin, and NOACs. When we look at evaluation metrics, we're mostly looking at intervention benefit, where we're just looking at the difference in expected reward for a given algorithm versus NOACs, and we normalize by that same difference with respect to threshold Whittle, which is sort of the best you could do because it's fairness agnostic. We also try to think about, all right, fairness, right? How can we say that our algorithm is more or less fair? So we look at Earth mover's distance, which for this particular setting is basically saying what's the cost of transforming the distribution over pull counts from my algorithm to the distribution over pull counts represented by round robin, in which case every arm would have an equal number of pull counts. So a higher value here is worse, in contrast to intervention benefit where you want a higher value. For data sets and how do we think about generating arms, we have two. The first is CPAP. So here we look at sort of a realistic setting where our transition matrices are derived from real patient data representing adherent and non-adherent patients respectively. And CPAP is an intervention that supports sleep apnea, so essentially trying to get people to use their CPAP machine. We also have a synthetic cohort so that we can have a bit more flexibility in transition matrix generation. We do require constraint satisfaction. However, other than that, those transition matrices are randomly generated. So when we look at the empirical results, we see that ProbFair is competitive with respect to the best, sort of fairness aware, but not guaranteeing alternative, which is risk aware threshold Whittle. It outperforms for certain values of L, and we only incur a slight loss with respect to intervention benefit. And I should say for higher values of L, it's essentially more fair, but we would expect, and what we observe is expected reward will decrease as we increase L. For each L and new combination, ProbFair performed competitively with respect to the best performing heuristic. However, it is interesting and kind of sad for us that in almost every case, the heuristics outperform. So the downside to the heuristic is that we don't get theoretical guarantees. However, the heuristics are state aware. We think that that might be having something to do with the fact that they're outperforming here. We also do some sensitivity analysis. So we look at varying the synthetic and CPAP cohorts, essentially making it harder for the algorithm to do well. So for our synthetic cohort, making it harder means increasing the percentage of convex arms. And all else equal, we expect that to decrease expected reward and increase earth move resistance. We see that this is true across the board, as figure 3 shows. We see expected reward in the left plot decreasing for all policies, including threshold Whittle, as convexity increases. And conversely, EMD is increasing. However, when we look at normalized results, so again, normalizing with respect to threshold Whittle, we do see that ProbFair is stable in terms of intervention benefit as well as earth move resistance. So pretty small variance there over many runs. We do similarly for CPAP. Here, the complexity comes as we increase the percentage of non-adhering arms, and results are quite similar, both quantitatively and qualitatively to the previous set of results. So again, stability here we consider to be a positive because we're basically saying even as the cohort becomes increasingly difficult and we see performance degrading for all policies, normalized difference will be relatively static. Finally, we investigate the price of state agnosticism. So if you recall from when I talked about how we construct ProbFair is stationary, it's also state agnostic, meaning that the mapping from arms to probability values does not change regardless of the state of the arm at time t. Threshold Whittle and all of the other Whittle-based policies we consider, including the heuristics, are state aware, meaning they're better able to take advantage of time-varying information in the problem. So we might think that this would be sort of a catastrophic thing, right? And we try to investigate the loss associated with the state agnosticism by constructing a version of ProbFair where we don't enforce fairness. And the way we do that is we set L equal to 0 and U equal to 1. So we no longer guarantee fairness, but we try to make these things, an apples to apples comparison. We see that ProbFair obtains about 97% of the intervention benefit and incurs a small increase in earth move resistance with respect to threshold Whittle. So we consider this loss to be acceptable rather than catastrophic. So I'd like to shift now to moving away from fairness for a moment to the setting where we have resource allocation over a community. And this is the second work called Network Restless Bandits with Positive Externalities. So another limitation of Whittle is that we cannot exploit spillover effects. So what does that mean, right? Imagine you're node C in this graph, and we give you a resource, right? Whether it's a call from a doctor or some type of health promoting thing, information, for example. It may be the case that C's neighbors derive partial benefit simply because C has received the resource. C, for example, might share information with some of its neighbors, B, D, or in this case, E, right? So ideally, we would like to be able to exploit these types of relationships because many real-world resource allocation tasks do take place within communities. So we introduced an extension of the restless bandit setting to address this case, which we refer to as networked restless bandits. So here, patients, similarly as before, are represented as arms. However, they are now embedded in a directed graph. We also introduce an augmented action space to encode allocative externalities. So if you recall, our state space is as before, right? It's binary. We look at do not exercise or exercise, but the action space now includes this option to message, right? Rather than just don't pull or pull. Now, I'll emphasize here that message does not have to be a literal message. Rather, it represents any action which is of intermediate benefit and intermediate cost with respect to a pull, and in particular that requires one of your in-degree neighbors to receive a pull to be unlocked. Meaning if we go back to our graph here, E is not eligible for a message unless C receives a pull. Our cost function is as before, except we now introduce this term psi, which is the cost of a message. And we require psi to be greater than or equal to 0, but strictly less than 1. And pulls, again, are unitful. So a nice consequence of the way we set things up here is that when our edge set is empty, we are actually able to recover the original restless bandit setting. So it's possible, though it's not tractable at scale, to represent the problem I've just described as a math program and sort of look at it from the perspective of constrained optimization. So in this setting, we have a decision matrix X, where we're trying to essentially map each arm to exactly one action at each time step. We want to maximize our total expected discounted reward, and our total cost cannot exceed our per time step budget as before. The novel thing that we introduce here is that a given arm I is only eligible to receive a message at time t if one of its in-degree neighbors gets a pull. Now, it may be obvious, perhaps, from how this constraint is expressed, that we cannot ensure satisfaction of it if arms are decoupled. This is because, how will we know if my neighbor has gotten a pull or not, if I'm considered completely independently, right? So this is sort of a problem in addition to the intractability constraints we raised earlier, right? So how do we think about a graph-aware solution? If we're not able to decouple arms in the network setting, however, it is possible to compute two sets of Whittle indices for each arm. How can we do this? We can basically consider each of our possible active actions, message and pull, as separate instances of a two action, so no act or message, no act or pull problem. From there, we can construct an augmented graph, and we can think about cumulative subsidies. So rather than thinking about what am I giving up, what's my opportunity cost of passivity as an individual arm, I can now think about directed edge pairs. So if I have some node U to node V, right, I'm basically going to say, all right, what am I giving up if U forgoes a pull and V forgoes a message? And importantly, I'm going to consider all pairs, which means that if, for example, there's a bidirectional edge between U and V, I'm going to think about pulling U and messaging V, as well as the alternative, so pulling V and messaging U. And the reason we call it augmented is we also introduce this sort of placeholder node, which is our -1 red node in G prime here. And what that allows us to do is to consider cases where we don't message at all. So for example, the 0 to -1 edge would represent pulling 0 and not doing anything else. And the reason we want to do this is because there are cases where it's actually not beneficial to message, right? The cost to relative benefit may not favor messaging. You may want to sort of use all the budget you have to dedicate to pulls. We want to be able to handle that. So the algorithm that we construct to address this situation we've constructed is called Greta. So Greta is graph aware, and it's a Whittle-based heuristic algorithm. And the way that Greta works is we begin with our augmented graph and our full budget and our pre-computed Whittle indices for each of our active actions. So those are our W1 and W2 here. And as long as we have budget remaining, and as long as our augmented graph edge set is not empty, what we do is in line 5, we consider our remaining budget, in chunks of 2. So for each chunk of 2 that we have, we say, okay, what's the best I could do in terms of my value function if I allocated those 2 units of budget only to pulls? So this is essentially saying, if I just consider this chunk of 2 in my augmented graph and apply baseline Whittle indexed, right? Who would I pull and what would my expected reward be? We do the same thing but we consider polls and messages as possibilities. And this essentially is requiring us to sort of enumerate over each node's neighborhood. We then compare those two things, and we choose the max valued candidate actions. We update our candidate action vector, our budget, by decrementing it, and our graph set by removing the corresponding edges. And we continue to do that until we run out of budget. So it's really a pretty simple algorithm. One of the nuances that we introduce to handle the fact that in this particular setting, while it is a graph, taking advantage of centrality is actually not sufficient, because it's possible, for example, that a high degree node could be connected to many nodes that are just not responsive to the intervention in question. So you might sort of over allocate to that subgraph if you focus on centrality by itself. But we do think, there are going to be cases where that's not true, and where a high degree node is also having connected to other nodes that really need the intervention as well. So we want to be able to handle both cases. So if we sort of observe, if we pull U and we decide to message V, but we still have some budget left over, we're not going to have to pay the cost of pulling U again. So it's actually possible to message remaining vertices V prime in the out degree neighborhood of U without incurring additional pull costs. So to sort of capture this possibility when we're considering our individual edges, we sort U's out degree neighbors by their index values, and whichever single edge is the max valued edge, we actually just represent that by the cumulative budget feasible value of the whole neighborhood. So we're sort of taking account centrality, but we're doing it in a way that incorporates the information we have about transition dynamics within subgraphs. So when we think about the theoretical properties of Greta, we are able to lower bound Greta with message costs of psi greater than 0 by the graph agnostic threshold Whittle. And this property follows from how we construct Greta. If you think about line 6 here, we're essentially going to sort of naturally degrade or sort of default back to threshold Whittle when it's not advantageous to consider messages. And that's sort of a deliberate choice there. And we can also upper bound with Greta where psi is equal to 0. And this is because we can message at least as many arms, right? When psi is equal to 0, we can basically get a lot of messages for free. Additionally, we can show that Greta is efficiently computable and time polynomial in its inputs. There's detailed analysis for that in the paper. I will also sort of share that when we think about sort of the qualitative findings of the runtime, Greta is designed for small graphs, and it will not perform terribly well at scale, and particularly for like web scale dense graphs. So that's a limitation of the approach we've constructed. Something that we're aware of, we acknowledge, and it's sort of a virtue of the fact that we're considering this sort of peer intervention setting where graphs are generally controlled by and known to the decision maker and will generally be relatively small. And if you wanted to adopt it for social networks, for example, you will need to adopt some types of relaxation, particularly with respect to the neighborhood level enumerations. So like sampling or like deep reinforcement learning are probably things to consider there. For improving scalability. We do some empirical analysis as well for Greta. So our comparison policies here are similar to those we use for ProbFair. Again, we have, for example, threshold Whittle as our baseline, although here we sort of expect it to be a lower bound rather than an upper. We also have our baselines, which are graph aware in these cases. So we have random, we have centrality weighted random. We also have myopic. So myopic is just looking at the immediate next time step in terms of expected reward, rather than taking into account the expected discounted reward over the full time horizon. Finally, for very small values of V and E, we are able to solve the constraint optimization problem that I presented earlier via value iteration. So that is the exact optimal solution to the system level MVP problem. And again, it's only possible for small graphs, but it's a nice sort of sanity check. When we think about arm generation, similarly here, our transition matrices are random, subject to structural constraint satisfaction. In this particular setting, the choice of how we map arms to positions in a graph is actually quite important. It has sort of an impact on results, and it's not something you can sort of just trivially decide. So we try to be mindful of that. We use a stochastic block model to produce a graph with n vertices. And then we sort of think, all right, how can we partition vertices into blocks such that we can then stochastically insert edges and corresponding with our parameter choices here, right? So we consider two options. One is random, and the second is by cluster. So for random, we can think about that as like a randomized controlled trial, for example. So this means that arms might be connected to people that are very different from them with respect to transition dynamics. When we think about by cluster, we actually cluster the arms using their transition matrix entries. So here, we're like the probability of an in-cluster edge is basically saying you're more likely to be connected to someone with transition dynamics similar to yourself. And it's a relatively high dimensional when we think about transition dynamics. We have a tensor over the action space, but still similarity as opposed to either randomness or divergence. So when we look at our results, the first one I have here is Greta versus the optimal policy. So because we're looking at value iteration for the exact optimal solution here, we use a very small graph. We specifically consider 8 arms in a fully connected graph. And we observe that Greta outperforms threshold Whittle, and it's competitive with respect to pi star, which is the sort of teal uppermost line here. Notably, Greta is not optimal. We don't expect it to be optimal. We don't claim that it's optimal. We just claim that it's constrained reward maximizing and that it can be lower bounded by threshold Whittle. So there's still some room for more innovation in this space to sort of improve and approximate with the value iteration solution. We also compare for larger graphs, again, sort of moving away from value iteration, Greta versus alternative policies. So here we're looking at a graph of 100 nodes. We see that Greta outperforms graph agnostic and graph aware alternatives. And this is true for both mappings from arms to graphs, so randomly and by cluster. And myopic is, I think in both cases here, the best performing graph aware alternative, which is not terribly surprising, but it might be interesting to note that, the centrality weighted, as we're sort of alluding to earlier, doesn't actually do as well as we might expect. And that's because of the fact that arms can be connected to people that are different from themselves. We conduct sensitivity analysis with respect to the budget and the message costs. So we see that Greta outperforms for all values of budget that we consider. And in the rightmost plot here, as we increase message costs, psi, we see that the expected reward from Greta is the gap rather is highest when the message cost is 0. This makes sense because messages are free. So this is really the best case scenario for Greta. And we see performance sort of gracefully degrades until it converges with threshold Whittle for values of message cost around 0.75. And the intuition here is that as the message cost approaches 1, it's really not going to ever be better to use your budget for a message than a pool, because you're going to have some divisibility issues and you're going to end up with remainders that you're not able to allocate. So this sort of pushes things in the direction of baseline threshold Whittle. Finally, we conduct sensitivity analysis with respect to assortativity. So here we observe, so in the leftmost plot here, we're basically holding P out for our stochastic block model fixed, and we're varying P in, so we're increasing it, right? So we're basically saying you're more likely to be connected with nodes similar to yourself. We observe that homophilic clustering with respect to transition dynamics might actually decrease expected reward by inducing competition. And what we mean here is that if you compare the leftmost plot to the rightmost plot, where we're varying disassortativity, so the probability that you're connected to an arm that's dissimilar to yourself, we see that in both cases, there's a gap, Greta is outperforming, but that sort of levels off for assortativity, but continues to rise for disassortativity. And we think that heterophilic clustering, so increasing disassortativity, is sort of helping to smooth out our subgroups' relative demand for the resource in question. Essentially, we're saying, okay, some part of the subgraph is getting the resource at time t, and the need or relative demand is varying in ways that's not true when you're connected to people that are most like yourself. All right, so that's sort of the conclusion of my talk. I'll end on some takeaway points here. The first of these is that if you're able to carefully incorporate prosocial constraints as we do in prop ver, we can improve algorithmic acceptability. So we saw in that setting that we're able to sort of ensure rationality of participation in expectation for all participants without unduly sacrificing utility for the group as a whole. We're also able to do that in a way that's tractable if we move slightly away from time index fairness toward probabilistic fairness. And in the second part of the talk, we've shown that when we exploit structure, we're able to take advantage of positive externalities when they exist, when we look at resource allocation over communities. So thank you all for listening, and thanks as well to my advisor, my co-authors, and to Penn State for hosting me for this talk. My contact info is here, and I'm happy to take questions.
Okay, thank you for Christine's talk. So next, let's move to the QA session. Today we have Ginny as our discussant. So shall we start with Ginny? And if any others have questions, we can do that after her.
Sure,
okay.
Sounds good.
Hi, Christine. My name's Jeannie. Thank you so much for the talk. I think it's definitely a very valuable contribution to the field of fair allocation. And to me, because I personally works with social media data, so I can totally see intersects with, like the like information diffusion models that we've been using. So like I mean, I can see the like applications to it, like just model information diffusion, because I personally work with misinformation, so I see informations of it. But then it comes to some of my questions about the model itself. So first, I just, because here because I personally more interested in the positive externality because it's more common compared to fairness allocation. But I'm just wondering, like, I mean, you've assumed in the model that the information is the communication is instantaneous, right? Like there's no delay in the information diffusion, but in the real scenario, there's definitely like delay, and there's like misinformed. There's definitely uncertainties, noises that comes within the actions, and also they're like the information they're trying to communicate with with their neighbors. So I'm just wondering whether you've considered the robustness of this model when it comes to the changing those behaviors, and also whether the information itself is true, because at least in this case you've assumed that the information you've diffused is definitely true, and they know the entire picture, but most of the case they don't really know the entire picture.
Yeah, that's a really good question. So I think there's a couple of ways we could tackle it, right? And before I get into those, I'll just emphasize a little bit that it doesn't have to be information, but it can be. We actually have a workshop version of that paper where we do look at misinformation. So there the intervention is sort of like some type of human fact checking versus like a cheaper, automated classifier to flag content. So the assumption that you're highlighting is basically the fact that we're saying, for example, when I tell you to message someone, you're going to do it, right, with probability 1. So that's, of course, something that is, like you say, right, not necessarily going to be true. There also might be this issue of lag or noisy transmission. So the probability that it might fail is something that you could introduce into this model, I think, with it would be a fairly straightforward extension by introducing edge weights. The reason that we didn't do that is because if you think about from like the hyperparameter perspective, right, we already have transition matrices, which are, entries per arm, which are random. We also have the stochastic block model. So there's already a lot of stochasticity happening. And the notion of how do we properly choose these edge weights, we didn't really have a good intuition for what would be a reasonable choice there. So we sort of defaulted to 1. And I agree that's like the best possible case, and it's not going to hold in practice. For me, like a dream situation for this work would be to have some type of real world longitudinal social media data that we could actually sort of, learn from, look at how can we develop realistic transition matrices, and sort of, I think there are many things you could do if you're thinking about it more empirically for behavior types at the user type level. For example, like if you're a bot versus if you're a well-meaning person who sometimes gets fooled, right, and shares misinformation by mistake, and sort of everywhere in between that spectrum, right? But you're absolutely right to highlight sort of the relationship to diffusion models. It's slightly different in the sense that we have this notion of transitions over time, but it might be the case that for a lot of real world agents, the types would be relatively static. Like you're either always sharing misinfo or you're seldom, for example, right?
Right. Sorry, I have like a follow-up question with this as well, because I've seen like, like the experiments you've conducted mostly like, on a smaller scale, but like when it comes to like social media, it's like the N could blow up really fast. Like it could be really, really huge. And I'm just wondering if I saw that you've conducted some real life scenarios, some data I've used, I think for the first model. I'm just wondering like what is the scale of that real life scenario testing, and also like how it can be scaled to like like social media.
Yeah, that's a good question. So unfortunately, I think that's the answer is probably like a future work question. This work is definitely application inspired or motivated by these real world settings, but we don't have it doesn't scale high enough to handle web scale data, right? Like the performance is just not there. And that's because we're doing sort of brute force enumeration over neighborhoods at the node level. Now, this could be, of course, parallelized, right, over nodes, but you're still sort of bound by the node with the largest neighborhood. And when we're talking about social media, that could be extremely large, right? So I do think that to move forward in that direction, you would either have to consider sampling strategies, at the neighborhood level, or perhaps just move toward a more, deep RL style approach. And I do think that could be the path forward here. Just haven't had time to do it yet.
Thank you so much. Thank you.
Yeah, thank you for the questions.
No problem.
Is there anyone has questions? Okay, I think we could be we could done for today's talk. So thanks again for Christine's talk. Before I end today's talk, let me make a short announcement. So for our last talk in this semester, we will have Serena from UC Berkeley to share her research. Her research is focused on understanding and improving the long-term social impacts of machine learning by rethinking machine learning algorithms and their surrounding incentives and practice. So her talk will be held on April 20th. If you are interested, please consider attending. Okay, thank you everyone. Bye-bye.
Thank you. Take care. Bye.
Thank you.